When Euclid vanished into history, his voice could have been lost forever. And yet, against fire, conquest, and time, his elements endured. Preserved by Byzantines, translated by Arabs, rediscovered by Europe, it became the backbone of global learning. This is the story of Euclid's afterlife, how a book from ancient Alexandria shaped the destiny of science, and how, in the end, the universe itself proved stranger than Euclid ever dreamed. Euclid himself vanished into silence, but his book, The Elements, refused to die. Copied by scribes, translated across empires, it traveled farther than Alexander's armies, farther than Ptolemy's ships. From Byzantium to Baghdad, from Oxford to Florence, from Newton's England to Kant's Königsberg, Euclid's geometry became the bedrock of civilization's quest for certainty. After the decline of Alexandria, the Byzantine Empire became the first great guardian of Greek science. Scholars like Theon of Alexandria and his daughter Hypatia edited and commented on Euclid's texts in the 4th century AD. Hypatia's commentaries on data and elements helped preserve them through the centuries of turmoil that followed. Byzantine scribes saw Euclid not as abstract curiosity, but as practical knowledge, useful for astronomy, land surveying, and architecture. In their hands, Euclid's proofs survived the collapse of Rome and the Dark Ages of Europe. Without them, the thread might have snapped forever. In the 8th and 9th centuries, the Islamic world ignited a new dawn of knowledge. At Baghdad's House of Wisdom, Euclid's Elements was translated into Arabic by scholars like Al-Hajjaj ibn Yusuf. Later, Thabit ibn Qurra refined the text, adding commentary and expanding on proportion theory. For mathematicians like Al-Khwarizmi, Omar Khayyam, and Ibn al-Haytham, Euclid was foundational. His geometry underpinned algebra, optics, and astronomy. To Islamic architects, his rules guided the design of mosques and palaces. To philosophers, his deductive structure became a model for reason itself. Arabic scholars didn't just preserve Euclid, they tested him, extended him, challenged his postulates. Their work prepared the ground for both Renaissance Europe and the eventual birth of non-Euclidean geometry. In the 12th century, a new chapter began. Crusaders and traders brought Arabic manuscripts to Europe. In Toledo, Adelard of Bath translated the Elements into Latin, declaring proudly, "I have transferred this book from Arabic into Latin words." For the first time in centuries, Europe had access to the full architecture of Euclidean geometry. Monastic schools and later universities like Paris, Oxford, and Bologna built their curricula upon it. By the 13th century, Campanus of Navarra's Latin edition was standard reading across Christendom. The Renaissance brought Euclid into dialogue with art. His optics, long overlooked, inspired the mathematical perspective that transformed painting. Brunelleschi, Alberti, Leonardo, their vanishing points were Euclid's lines of sight. Printers like Ratelt of Venice produced the first beautifully illustrated editions of Elements in 1482. Geometry became not just scholarship, but art. The clean lines of Euclid mirrored the rediscovered clarity of antiquity itself. In 1687, Isaac Newton published the Principia Mathematica. Its structure was consciously Euclidean. Axioms, definitions, propositions, proofs. Just as Euclid deduced the universe of geometry, Newton deduced the universe of motion. For Descartes, geometry merged with algebra into analytic geometry. For Kant, Euclidean space became the framework of human intuition, the stage on which experience itself unfolds. To Enlightenment thinkers, Euclid was not just mathematics. He was certainty incarnate, the very embodiment of rational order in a chaotic world. For centuries, to study mathematics anywhere in the world meant to begin with Euclid. British schools required students to memorize his propositions. In America, Jefferson and Lincoln studied him as moral training in logic. In India, his axioms became part of colonial curricula. Euclid was the universal teacher shaping billions of minds. No single work of science has had such a sustained role in education. From 300 BC to the 20th century, Euclid was the constant companion of every educated generation. And yet, a storm was brewing. For centuries, mathematicians struggled with one postulate, the fifth, the parallel postulate. Could it be proved from the others? Was it truly necessary? The attempt to tame it would, in time, break Euclid's universe open and launch the greatest revolution in geometry since his own day. For over 2,000 years, Euclid's geometry was seen as absolute truth, the very shape of reality. But one postulate always troubled mathematicians. The fifth, the parallel postulate. Euclid's fifth postulate reads, if a straight line falls on two others, making the interior angles on the same side less than two right angles, the two lines, if extended indefinitely, meet on that side. In simpler words, given a line and a point, not on it, there is exactly one parallel line through the point. To many, this seemed less self-evident than the others. Was it really necessary? Could it be proven from the first four postulates instead? From Proclus in the 5th century, to Omar Khayyam in the 11th, to Sacheri in the 18th, generations tried and failed. In the early 19th century, Carl Friedrich Gauss suspected a shocking truth, that the parallel postulate might not be necessary at all. But fearing scandal, he kept his insights private. It was left to János Bolyai in Hungary and independently to Nikolai Lobachevsky in Russia to publish the unthinkable. They built a consistent geometry where, through a point, not on a line, infinitely many parallels can be drawn. This hyperbolic geometry did not contradict itself. The Euclidean universe was no longer unique. In hyperbolic geometry, space curves away. Triangles have angle sums less than two right angles. The familiar rules bend into strange, elegant forms. Then came Bernhard Riemann. In 1854, he unveiled a geometry for curved surfaces of any dimension. Spherical geometry where no parallels exist. Hyperbolic geometry where countless do. A whole family of geometries, all as valid as Euclid's, all depending on the curvature of space. Riemann redefined the question itself. Geometry was not about absolute truth, but about which axioms match the world we inhabit. 60 years later, Riemann's vision became the key to physics. Albert Einstein used non-Euclidean geometry to describe gravity itself, not a force, but the curvature of space-time. In Einstein's universe, triangles drawn near stars have angles greater than 180 degrees. Space itself is pliable, curved by mass and energy. Euclid's postulates still hold on small scales, in classrooms, on city streets, but for the cosmos, new geometries reign. Even before Einstein, Euclid's legacy had been rebuilt. In 1899, David Hilbert reformulated geometry with precise symbolic axioms, eliminating hidden assumptions. He proved that Euclidean geometry is consistent, provided arithmetic itself is. Euclid's method, start with axioms, proceed to proofs, survived, purified for a new age. The crisis of the parallel postulate gave birth to whole new geometries. It shattered the illusion of one absolute mathematical truth. It forced us to ask, is mathematics discovered or invented? Do axioms describe reality or merely possible worlds? In breaking Euclid, we did not destroy him, we fulfilled him. His method, to test, to deduce, to follow logic wherever it leads, was precisely what allowed his heirs to step beyond him. Today we live in a multiverse of geometries, Euclidean, spherical, hyperbolic, applied in architecture, physics, computer graphics, navigation, cosmology. Euclid's fifth postulate, once a thorn in his system, became the gateway to the geometry of the universe itself. 2,300 years after Euclid, his lines still guide our hands. Every building, every bridge, every screen we touch echoes his geometry. From the chalkboards of schools to the algorithms of computers, Euclid endures. He has become the quiet architecture of the modern world. In physics, Euclid remains the starting point. Engineers calculate stresses with his theorems. Surveyors map land with his triangles. In space exploration, his geometry guides satellites orbiting Earth. And yet, the legacy runs deeper still. Relativity, quantum field theory, cosmology, all stand on axiomatic structures that trace their lineage back to Euclid's method. His idea was not merely geometry, it was proof. The notion that from a few self-evident truths, the universe could be deduced. In computer graphics, Euclid's constructions underpin every polygon. Video games render worlds with triangles and vectors. Algorithms in cryptography rely on his proof of infinite primes. In an age of quantum computers and artificial intelligence, the foundations are still Euclidean. Every 3D model, every CGI effect in film is built on Euclid's methods of projection and transformation. His geometry has become digital. For philosophers, Euclid was a mirror of certainty. Kant believed Euclidean space was hardwired into human intuition. Bertrand Russell and Alfred North Whitehead modeled their Principia Mathematica on his method, seeking to ground mathematics in pure logic. Even debates on whether mathematics is discovered or invented begin with Euclid's ghost. Euclid symbolized the dream of absolute truth, and his unraveling showed us that even truth can have multiple forms. Beyond science, Euclid haunts culture. M.C. Escher twisted Euclidean grids into paradox. The novel Flatland used geometry to imagine higher dimensions. Freemasons adopted Euclid's tools, the compass and square, as symbols of moral order. In cinema and science fiction, parallel worlds echo the parallel postulate. Even in art, we live in Euclid's shadow. Geometry is more than mathematics. It is our attempt to read the universe. When we trace a circle, we echo the orbits of planets. When we prove a theorem, we glimpse the order of galaxies. Euclid gave us the language to see the cosmos as intelligible, to believe that knowledge could be certain. And yet, he also taught us humility. His silent life reminds us, it is not the man that matters, but the method. The proofs outlast the author. Truth, once spoken, belongs to all. Euclid's biography is lost, his face unknown. But his voice still speaks every time a student draws a line, every time a proof is read, every time the universe is measured. His work has outlived empires, languages, and religions. What he gave us was more than geometry. He gave us the very idea of certainty and the courage to test it. In the Cathedral of Human Thought, Euclid was the first great architect. His stones are still in place, and they will stand as long as minds seek truth.